Hello and welcome. In this video, we are going to take a look at contour plots. Contour plots are another way of visualizing multivariable functions. So far, we have seen them by using cross sections of z versus x and z versus y. So with z versus x, we hold y constant at some value. And when we look at z versus y, we hold the value of x constant at some value, thereby successfully reducing our three-dimensional problem to a two-dimensional one. However, since we have three variables, it seems reasonable that we could say, well, instead of holding x constant or y constant, what if we wanted to hold z constant instead and be able to visualize the corresponding relationship between x and y? So if that's of interest to us, let's first start off by taking a look at a picture of the following hot air balloon. And suppose we created a series of horizontal slices through it, all of which are equally spaced. To keep things simple, we assume the balloon will not deform in shape in any way whenever you slice it. So imagine that we sliced this hot air balloon at these four different points. And you can see that these are pretty much equally spaced. And that's important because at different heights along this balloon, we want to plot the corresponding shape of what we would see. Now, depending on how you visualize this, usually these are kind of have more of a rectangular base when you think about the there we go. So this is kind of your hot air balloon here. So let's imagine this represents sort of a rectangular base. So if I were to create a slice at z equals 1, and I created that slice right about here, and then what I did is I separated those two pieces, and I looked down at this portion that I cut, and I just wanted to look at what the shape was around that seam where I made that cut. Then what I would see is something roughly rectangular. So let's pretend that this is our z-axis coming up here. And so what we would see in terms of the x versus the y is we would see something that looks a little like this. Okay, now that's just what we would see if we were to slice at that pink line and then take a look down at the resulting basket. So we would see, again, opening this up and looking down, we would see something that looks like this, right? And then the top portion, which contains the balloon up here, we separate those two pieces. And so here is that seam that I'm referring to. That's the seam that you would see when you chop this and you look down upon it, you would see kind of this type of shape. So that being said, we could also slice it at different points, like z equals 2. And if I sliced at z equals 2 and then look down, what I would see is something that's circular. So this would be, I'm trying to draw that circular shape here that you would see if you created that cut right there. And so at z equals 2, this is for z equals 1. For z equals 2, the relationship between x and y that I would see is some sort of circle. Now I'm going to draw this circle with that's a little bit larger than the base here, because we notice that the circle flares out in the left and the right directions farther than does the actual carrier. So that means that we should at least be able to keep these somewhat relative to one another, where if that represents the basket, again, we're looking from the top down onto this basket, but then if we slice that balloon at that one point, we would see a circle that's slightly bigger than the square is itself. Now, if we sliced at z equals 3, similar type of situation, except we would see a circle that is quite a ways wider than the smaller circle down here. And so the contour that we would see would still be circular in shape, but it would be a little bit bigger. Now, we're not trying to be super accurate here, but just to be able to see the pictures relative to one another. Finally, if I were to cut this at z equals 4, right about there, I notice that width is a little bit less than the width here, but it's a little bit more than the width here. So actually this circle for z equals 4 will be somewhere in between the size of the circle at z equals 2 and the circle at z equals 3. So I'll draw it a little bit smaller than the z equals 3 circle, but a little bit bigger than the z equals 2 circle. Now, typically what we want to do with these are called contours, and a contour is what happens whenever you take these horizontal slices and you look down at the surface and try to visualize what you would see. And that is described as a contour when it's in the xy plane. When we take the contours and put them on the same set of xy axes, we have created a contour map. That is, we now have a two-dimensional reduction of a three-dimensional graph. For one, we have preserved the z values, but we have done so in such a way as to create it in a two-dimensional representation. Note that it is important that the z values be equally spaced for easy reference. So we had z equals 1, 2, 3, 4. The spacing between them could be z equals a half, z equals 1.5, z equals 2.5, but the step size between the different z values should be kept the same to preserve some niceties of that graph. Otherwise, if you don't equally space them, it's hard to really understand what's going on. You'll see what I mean here in a moment. So now for these different graphs, if I put them together, so if I had my little carrier here, and then the slightly larger circle that represents what we would see if we sliced at the elevation of the balloon, and then the slightly larger one, and then the one at the very top. So here's kind of what we would see. And then what we would want to do is label these. Of course, we'd want to call this z equals 3, and then this guy would be our z equals 4, and z equals 2, and lastly, z equals 1. So this is our very first contour map. Of course, we want to apply these to functions. So if we take a look at just this representation here of something that looks like a downward face opening paraboloid, and you can see that depending at what elevation you go, for example, here we have an elevation of 40 units. So if you were to walk along this trek, along this black curve, you would be maintaining a steady elevation of 40 units. Similarly, up here, if you were at an elevation of 110, you could be at any point along this elliptical ring, and that would maintain an elevation of 110 feet. So if you walked in that ellipse, you would never be changing your elevation. You'd be hiking on a flat plateau. Of course, to go from contour to contour, if I went from here and I walked this way, well, clearly that's going to reduce my elevation from 110 units down to 100 units. Now imagine that each of these slices, imagine we have a slice at z equals 40, z equals 50, all the way up to z equals 110. Imagine that at each of these slices, we looked at that seam. That would basically be the seam where if we sliced through at an elevation of 110 feet, we would basically chop off this little egg-shaped piece. And imagine that we took that shape and we projected it down onto the xy plane. Recall that, and without loss of generality here, if this was x and this was y, and then this is our z-axis, that what we're doing now is we're visualizing for that particular value of z equals 110, what does the relationship of x and y look like? In other words, what's the set of all points x comma y where my elevation maintains at 110? Well, it's all the points along this egg-shaped object. So to begin understanding this, so here is kind of an image of a different paraboloid to give us the sense of what's going on. Why do the contour rings, so each one of these is a contour ring, appear to get closer and closer together as we move away from the origin, even though each ring is an equally spaced z-slice? Notice that each of these contours occurs every 2 units of z. So we have this circle represents all the points in the xy plane where z is 2, all the points xy where z is 4, and then 6, and 8, and 10, and 12. But the one thing that we do notice is that as you move further out, if you move in a straight line, then the distance between this contour and this contour is fairly sizable. But between So that's between a contour of 2 and 4, but from an elevation of 4, we'll just say 4 feet to 6 feet, that's a lesser distance in the XY direction. Similarly, between 6 feet and 8 feet, we have to travel a shorter distance to get that same 2-unit jump in my elevation than we did back here. Here we had to walk a lot farther to get that 2-unit increase in our Z value. And you can see that the farther out we move, the closer those contours are together. In other words, the shorter the distance we have to walk in the XY plane to make it to the same elevation change as before. So for instance, here we have just sort of that three-dimensional surface, and here you have this plane that's sort of acting as the knife that slices this paraboloid at z equals 2. And if this is the function f of x comma y equals x squared plus y squared, then we can think of this as, well, what are all the ordered pairs x and y that make our function have a constant elevation of 2. And the one thing that we remember from, hopefully, from our algebra is that x squared plus y squared equals radius squared. And that's going to represent the shape of a circle. So in this case, if we rewrite this as x squared plus y squared equals the square root of 2 squared, then that represents all the points where it's going to be a circle with a radius of 2 units, square root of 2 units. So that radius right there is square root of 2 units. And the bigger we make the value of z, you can see that the circles get larger and larger because the paraboloid is growing outwards away from the origin. So you can see that this circle here, this ring, is going to be larger than that circle, and this is going to be the largest of those circles in that picture. So again, we're looking at it from top down. So if I were to create this slice here at z equals 6, separate the top and just look at that, I would see that one ring right there. So in a sense, we can draw these contour plots by physically replacing a number in the equation, in this case for contour plots the value of z, and then plotting that relationship between x and y. So the thing that we're going to reason through here is the reason these contours get closer and closer together is look at what happens to the steepness of the curve. If you were to kind of look at this as a two-dimensional parabola, we know that the slope right there is less steep than the slope right there, is less steep than the slope right there. So on a parabola, as you move farther away from the origin, these slopes get steeper, which essentially means that if the slope is steeper, then I don't have to take as big of a step to get 2 units higher than, say, I did back here. Here to get 2 units higher, that might be this distance, but here to get 2 units higher, that's only going to be that little tiny distance right there. So to get from contour ring to contour ring, this is telling us that as we move further away from the origin, here we have a very flat, kind of a more flattish bowl. As we move away, that bowl starts to get very steep. So we can also visualize this in our contour plot applet. And now this is the same applet as in our lesson on cross sections, but in this applet, we can now take a look at holding the value of z fixed. So here we have that upward opening paraboloid. And depending on where we look at the value of z, if we now set the value of z, right now we're in the negative realm, so there's no cross section because this paraboloid is only defined for positive values of z. So you can see here now, if I set z pretty close to 1, we'll say 1.8, that's going to be all the xy points where when the square of x is added to the square of y, we get a z value of 1.8. Now you can kind of see where that is. If we create that slice right through this point, in fact, if we look down on it, this blue circle is essentially where our contour is. That's the size of our contour. And as we increase that, as we change the value of z to higher and higher points, those x and y pairs fall along circles that have a larger radius. You can see it here very clearly. And you can see that now we're cutting this paraboloid near the top of of our range. And it's as if kind of water filled up inside of there to that elevation. Well, it would form a circular pool. And if that water was really shallow, because that bowl is very flat towards the bottom, you're going to have a smaller pool of water in which to swim. Well, the idea of contours is not just unique to mathematics. In fact, when you're studying geography, you are looking at topological maps. Now, topological maps are used to distinguish different elevations. So this is South Hamilton, New York, and this is a topographical map, and you can see the different elevation contours marked out. So if I want to be at an elevation of 1,300 feet, you can see sort of, here's the 1,300 contour, and I can follow that along and see all the different places where the contours are 1,300. Now here they kind of skip a little bit. Here's 1,311. I'm not really sure why they chose to do an 11-foot change in elevation, but there must be some good reason for why they did that. And you can kind of see if you were to go, if you were a hiker, and let's just say some of this was hiking space, I'm not familiar with this region, then you can kind of see where, how much of an elevation change you would have. So if I started at this contour ring and made it up to here, that would be about a 300-foot elevation increase from there to there. Not much of a hiking region overall, if you think about it. 300 feet is not a terrible change in elevation, but nonetheless, it shows us how the mountainous regions are laid out. Let's take a look at another example. The contour plot below gives corn production. So C is a function of R and T. So R is the amount of rainfall. So of course, corn production is going to depend on how much rain you get, and on the average temperature. So if it's too cold or too hot, you're not going to get a high yield of corn production. Use the contour plot below to estimate f of 18,78 and f of 12,76. Let's spend a moment making sense of this. Along the horizontal axis, we have one of the inputs, which is the amount of rain. So we can see what would happen if we had 6, 9, 12, 15, 18, 21, or 24 inches of rain in a season. And then what the average temperature is, starting at 72 degrees Fahrenheit all the way up to 80 degrees Fahrenheit. Now the blue contours show us for example, this entire blue contour ring right here, that's where I will be able to yield 80 units of corn. C was not defined as how we're measuring corn production, but we have 80 units of corn produced anywhere along this curve. So to estimate f of 18,78, what I'm saying is that I have a rainfall of 18 inches during that season, and I have a temperature of 78 degrees Fahrenheit. So let me locate that. 18 inches with 78 degrees Fahrenheit, and I want to figure out where those 2 points are. Well, that's going to fall right about there. Now, what does that mean? Well, that means that f of 18,78 is 100, and that means that if it's this many inches of rain, 18 inches of rain, and it's 78 degrees Fahrenheit, then we expect to get 100 units of corn produced. So if contour plots allow us to, again, look at three-dimensional functions, there would be very little difference in me actually looking at rainfall, temperature, and the resulting corn production, and seeing that this is essentially going to be some sort of maybe more of an elliptical paraboloid, but it may look something like this, where we can see that there's sort of the sweet spot. You can get 110 units of corn production as you get closer to this point here, which, well, let's say that represents about 19 inches and about 75 degrees. So this right here, if we project it upwards from there, that would represent what seems to be our max of about 19 inches of rain. We said about 75 degrees, corresponding to 113 units of corn produced. And then we can see if we get very little rainfall, like 6 inches, we're pretty much destined to get somewhere between 40 and 50 units of corn produced. Now, like, what happens right there? Well, right there is where I have 6 inches of rain, 72 degrees Fahrenheit average temperature, but I see that I'm somewhere about halfway between the 40 and the 50 contour. So I might say that as an estimate, there's no way to do this exactly, especially since things are not changing linearly, but since it's about halfway between 40 and 50, I could say that f of 6, 72 appears to be about somewhere around 45 units of corn produced under those conditions. So the other one we wanted to estimate was f of 12, 76. We have less rain, lower temperature, probably going to get a lesser yield, but let's double check. Here's 12, here's 76. 1276 falls roughly halfway between there. I'm going to guess it's about 85 units of corn produced. So less rain, lower temperature. Maybe the temperature is better, but having 6 inches of less rain probably is going to affect our yield quite a bit. So we can totally use these types of things to take a three-dimensional representation and reason through them in a very useful way. Example 4 says, use the contour plot above to describe in words the cross sections with T and R constant through the point representing present conditions. Give a common sense explanation of your answer. Okay, so what this is asking for is, we want to think about cross sections from a contour plot. How could we do that? Well, here we are at the point present. That's right now. For this season, we'll assume that there have been 15 inches of rain, 76 degree Fahrenheit average. And now what we want to do is try to think about the cross sections with respect to T and R. So to have the cross sections with respect to T, what I'm asking for basically is I want to look at the relationship between corn production and temperature by holding rainfall constant. So if I'm at that point right there and I hold rainfall constant, that means I'm going to be stuck with a rainfall of 15 inches, not degrees, and with 15 inches, I am looking at those temperatures right there. All right, well, let's think about how we would begin graphing this, or how we could begin sketching this. So here we have the temperature, and here we have the corn production, and we're going to denote that this is when R is fixed at 15 inches of rain. So in order to grab points from here, I could think about all of the places where my contours intersect with 15 inches of rainfall. And here is another one and another one there. And this allows me to gather ordered pairs. I know that all of these 1, 2, 3, 4, 5, 6 points, they all fall on 15 inches of rain. The only thing that's different about these points is how much temperature there is and what the corresponding production is. So at this point here, I have 15 inches of rainfall. The temperature appears to be about 70. I'm going to guess that even with that break in the graph, that's about 70 degrees Fahrenheit. So with 70 degrees Fahrenheit, I expect to have a production of 90 units of corn. So 70, we'll just go ahead and create a break in the graph, and we'll just say this is 70. And that corresponds to, what do we say, 90 units of corn produced. So again, I'll break in the graph, put 90 right there. There we go. Now, the next point that we have labeled, and we could interpolate between curves as well. It's just a little bit harder and less accurate to do. So here I have 15 inches of rain, about pretty darn close to 72 degrees Fahrenheit. So at 72, I have a corn production of 100. So 72, just increment this by units of 2. So 72, 4, 6, 8. So in 72, we are estimating 100 units of corn. And similarly, for the next point, 15 inches of rain still, because we fixed the rainfall. 76 degrees also corresponds to 100 units of corn produced. So no change from 72 degrees to 74 degrees. When we're on the next point, which is about, oh, I'm sorry, that was 76, not 74. We don't actually have any information on 74 unless we're willing to interpolate, but we're not going to go there with that. So there's 76, and 76 was this point. At about 78 degrees, I have a production of about 90. So 78 drops back down. So you can see that as the temperature increases, there's sort of a sweet spot between 72 and 76 for corn production. And then when it starts getting warmer than about 76, the corn production starts to fall. We might also be able to argue that at 74 degrees, which is here, that falls somewhere between 100 units and 110 units. So it looks like 74 degrees gives us an even higher production. So we'll just estimate that to be what, about 102, 103? So about 103, maybe I'll just draw it a little bit higher. And so we can kind of connect these dots and see what's happening to corn production versus temperature. We could do the exact same thing for corn production versus rainfall by holding the temperature constant. So now let's go ahead and look at corn versus rainfall holding the temperature constant. And what we're going to hold it constant at is the condition that corresponds to present. So if I hold temperature constant, you can see that at present the temperature is 76 degrees. So I'm going to be focused on every point that goes through the point present and has 76 degrees Fahrenheit. And the different rainfalls that correspond to those points will be these guys along that line. Okay, so those are the points that we'll try to focus on plotting. So my rainfall goes from about 6 to 24 inches. Maybe I'll just go ahead and go in units of 3. So 3, 6, 9, 12, 15, 18, 21, 24. And so we'll label this as 3, and this is 24. Oh, we'll go ahead and just write them in. Make it easier on ourselves later. Okay, and the corn productions that we have range as low as 40 all the way up to about 110. So we'll just go in increments of 10. We'll say this is 40, 60, 80, 100, 40, 60, 80, 100. Oh no, I wanted to go by, let's go by tens. 50, 60, 70, 80, 90, 100, 110. Perfect. So now we know that if we hold temperature constant at 76 degrees Fahrenheit, now we can grab points from here. So at about 6 inches of rain, we can expect 40 units of production. So 6 inches of rain, 40 units of production. Next point, this is about, I don't know, I'll estimate that to be about 7 inches of rain. We get 50 units of production. So 7 inches gives you about 50 units of production. That's about there. And next we need to consider the next point, which looks like to be about 8, and that's 60 units of corn produced, and then 70 units of corn produced for 9. So we'll just go ahead and label those. So 8 is here, and then this one is here. Now, as we get closer inward, so this corresponds to about maybe 10.5 degrees, about halfway between 9 and 12, 80 units of corn produced. So 10.5 is about, let's see, 40, 50, 60, 70, 80. So needless to say, we can see that as rainfall goes up, corn production goes up as well. But then we see that the spacing gets to be a little bit more farther apart, that you basically have to travel a longer distance. You have to increase rainfall by a lot more to get a 10-unit increase in your production than you did back here. So here we're at about 1390, 1390. You can see that the curve is starting to flatten out a little bit. We're not getting as much of an effect from that rainfall. And then 15 inches will get you to 110. sorry, 15 inches will get you to 100. So 15 inches is 100, and then 18 inches corresponds to 110 units produced. So you can see how this is starting to kind of flatten out a little bit. And so while rainfall increase does help corn production, 3 inches of rainfall is not always going to yield the same increase in corn production. So we can do some really powerful analysis, and one of the real critical things is this may just seem like a graph, but there's a lot of information in this, and the more we focus on holding something constant, the more we could see the relationship between any two variables that we want. Now this is using a contour plot to answer questions. How do we actually build these contour plots? Well, as we saw earlier, we just hold the value of z constant. So we have to decide where we want to start and where we want to end. So maybe I'll start at z equals 0, and I'll go up to z equals 10 with a change in z of 2 units. And for each of these different z values, I will draw the resulting graph. So here's what I'm going to do. I'm going to set the value of z constant, make myself a nice little table, and then I'm going to look at the function. So I will write, function. So if z is 0, that means I'll have 0 equals 2x plus 3y plus 1. Well, what kind of function is that? Well, the way it's arranged, it doesn't really appear to be, but it is actually linear. In fact, if you solved this for y, you would get, let's see, subtract 2x, subtract 1, you would get y equals negative 2/3 x minus 1/3. Okay, now what's that going to look like? Well, that's going to look like a line with a slope of negative 2/3 and a vertical intercept of negative 1/3. Okay, so here we'll just say this is negative 1. So negative 1/3, this will be its vertical intercept. It's our x and our y axis. And then we'll need to basically, let's space these. 1, 2, 3. So from there, we go down 2 over 3. So down 2 over 3, plot a point, and there's our linear function. Okay, close enough. There we go. And so I'm going to label this as the contour for z equals 0. Now I need to do z equals 2. Well, I'm going to get tired of solving this thing over and over again, so let me just solve this equation to make the process not so redundant. Let me just solve this equation for y. So if I subtract 2x, I have 3y plus 1, and then I subtract 1, z minus 2x minus 1 equals 3y. And then if I divide by 3, I'll get z minus 1 divided by 3 minus 2/3 x equals y. Now I'll explain why I did that in a second, why I put z minus 1 together as one fraction. And the reason I did that is because I'm going to be holding z constant. So z minus 1 is just going to be a number. So I'll have plus z minus 1 over 3. So really, the z value is just going to affect my vertical intercept. This right here is my y-intercept, or at least the y value of my y-intercept. So all of these different lines that we get for different contours, let me just go ahead and do this one in a different color. If this is for z equals 2, then I will have the function y equals negative 2/3 x, z minus 1, 2 minus 1 is 1, plus divided by 3 is 1/3. So this is just going to be the graph shifted up 1/3. So it'll be the same graph, but it will now go through a slightly higher point. All right, try to get this as close as we can and shift this down a little bit. There we go. And now when we do the same thing for, so this is for z equals 1, for z equals 2, excuse me. When we do this for z equals 4, we'll have y equals negative 2/3 x. So if z is 4, we have 4 minus 1 is 3 divided by 3 is 1. So we have negative 2/3 x plus 1. And that's going to be a line that, again, is parallel to these other two, but that happens to go through a slightly higher point. And this will be and these should all be equally spaced. My graphing ability is not fantastic, obviously, but this should be equally spaced. So maybe what I should do is take this guy down just a teensy bit. Well, close enough. So we get the idea. All right, so if we continued going in this fashion, what we would see is the line would be the same, but the vertical intercept would continue to grow for z equals 6, z equals 8, and z equals 10. Now, if we go over to our applet and we type in, and we wonder why these cross sections are linear, well, here's that plane. Here's that function. This is called a plane. We'll explore these in the next lesson. This is a plane. It's essentially the equivalent to a linear function in 3 dimensions. So you can imagine this is a bunch of lines glued together to form a flat plane. Now, as I begin slicing this thing at different values of z, you can see that the cross section is in fact a straight line. And let me rotate this to get my positive axes. But you can actually see that now that I'm looking down at the xy plane, we can see that, oh, that's our positive. Let's see, I want to look at this quadrant here. There we go. So we can actually see that where this line intersects is when z is 0, we can see that this line actually has that slope of negative 2/3, and this point right here is y equals negative 1/3. When I shift this thing up to z equals 2, well, close enough. This is where we notice that it was the same graph, but it goes through z equals positive, y equals positive 1/3. And when z was 4, that's where we saw our line go through y equals negative 2/3 x plus 1. So basically, when you're taking contours of a plane, you're generating straight lines. So if you have a contour plot that has equally spaced straight lines, and the reason they have to be equally spaced is because a plane doesn't ever change in slope. A plane has a constant slope all the way across. All right, now let's do one final exercise. And in this exercise, let's sketch a possible contour plot for this surface. So what this looks like is a parabola. And we notice that the reason this is a parabola is because notice that the cross section right there is identical to, say, the cross section right there. And it's identical to the cross section right there. How do we know that? Well, if we were to take a look at the graph from this perspective, we would basically just see a little tunnel. And we would see that this top is actually flat all the way across. That should give us some pretty good insight. So in terms of what kind of function this would be, well, the parabola actually only depends on the value of x. It does not depend on the value of y. We produce the same downward facing parabola. So I would say this is something like negative x squared plus, I don't know, whatever this value is right here. So we'll just say that's z equals 10, for example. This would be z equals negative x squared plus 10. All right, so having said that, if we now begin to slice this thing in different positions and different values of z, what would the resulting shape look like? So if you can kind of imagine creating a slice that will, I'm going to try my best here to do this, but if I chop through this thing, and I'll just sort of hide this piece here. If I were to slice this thing, one thing that I should notice is that where this plane intersects this paraboloid, or this, I shouldn't call it a paraboloid, but this parabolic function, that edge is a straight line, as is this edge back here. And if I were to lay that flat that plane flat on top like this, so imagine that this is my plane, the only thing that I would see here if I barely graze that top is just this one straight line. And depending on where I create that slice, if I created it further, down here, so if it were down towards the bottom, what I would notice is a straight line, once again, here, and a straight line over here. So what I would imagine is, in terms of my phase plane, or my contour plot, is when z is equal to 0, which I will assume that's right here, so this is where this parabolic function rests on the xy plane, I see two lines along the x that are perpendicular to the x-axis that lie kind of farther apart. So they're maybe here and here. Now I see that the slope is rising as x works its way inward. I see that this is a lot more steep than this portion of the curve is. So to get a constant change in elevation, I'm at first going to have to kind of move in quite a bit in this direction to get, let's say, like a 2-unit change in elevation. But those two lines that I would get on either side would be closer together. But now, as I move to get that same elevation change, I don't need to move over in the x direction quite as far to do that. So to get the same change in elevation, I only need to walk this short distance instead of this long distance to get that change in elevation. And then here right at the top, we would have a contour marker that looks like that. So here we'll just say this represents z equals 0. So this is z equals 0, and this is z equals 0. And we can kind of say that maybe this next contour is z equals 2, and z equals 2, and then maybe this one was z equals 3, and z equals 3. And then all the way into the center here, we just kind of arbitrarily labeled that z equals 10, just to have something to play with. And we can say that at z equals 10, we're going to have a plane that just grazes that top. Now, just to emphasize that this was in fact the graph of x squared. I'm sorry, this should be negative x squared, because it faces down, and we'll just say this is plus 10. Okay, so there's that parabolic function. Again, you can see that the value of y, the cross section, is always going to be the same, because that parabolic function is the exact same one regardless of the value of y. Now, as the value of x changes, now we get these different line segments. It's only highlighting, so with respect to x, what we see is these different linear functions. And when we change the value of z, so look at those two lines there versus when our z is lower, that plane intersects that parabolic function at two different locations that represent straight lines. And as I get closer to the top of that, I see I'm only going to have essentially that one line at z equals 10. Let's see if I can get that fine-tuned. There we go, z equals 10. So there you see that just one straight line that we get when z is equal to 10. So contour plots along with cross sections reveal a ton of information about data and our ability to analyze multivariable functions.